Okay, so welcome back. This is part 6 in our series where we help you to understand laptop motherboards, how they work, in case you want to just learn about them, or if maybe you want to repair them, you understand what all the components are, how you can understand what's going on so you can repair them. In the previous videos in the series, we talked about the DC input, the jack, how that's all configured, how the power management is configured to turn on and turn off the DC coming in from the wall adapter. We also talked about what you see here, which are the DC to DC converters that convert the 19 volts coming from the wall adapter into the lower voltages required by the components on the motherboard. We also talked about simulating those in LT Spice, which is a free electronic simulator program that is really important to learn if you want to understand electronics. So we showed you how to simulate these circuits. We also talked about some very important resources and tools and techniques that you will need if you want to understand what's going on your motherboard. So I encourage you to look at the previous videos in the series. In this video, we're going to go into a little bit more depth about this large section you see on your motherboard, which has the different, what are called the voltage rails, where we've got DC to DC converters that convert the 19 volts coming in from the wall adapter or the 12 volts from the battery down to the voltages required by the different components on the motherboard. And you can see here we've got these large inductors we talked about previously, and those kind of indicate different voltage rails that are being generated from the 19 volts. So we've got 1, 2, 3, 4, 5, 6 big inductors, which implies we've got 6 voltage rails here converting down to lower voltages. And we talked about, for example, this circuit here where we've got a 20-pin controller that switches these two MOSFETs and generates a PWM voltage, a pulse width modulated voltage on the input to this inductor. And the output, we've got some capacitors where it takes the PWM signal and filters it so that you get a flat DC of 1.5 or 3 volts or 5 volts or whatever. So this circuit you're going to see duplicated many times on your motherboard, as we can see here. However, there are always in the electronics world some variations. So for example, we have here right above it, we've got a controller. We've got what looks like one MOSFET, an 8-pin MOSFET and an inductor. And we talked about, well, this is actually 2 MOSFETs in one package. And we talked about that in the previous video. So I encourage you to look at that. But again, it's a controller, a couple MOSFETs, an inductor, and some capacitors. We also have up here, we've got a couple of MOSFETs, an inductor. Here we've got a couple of MOSFETs and an inductor. Down here, we've got 2 inductors and we've got a couple 20-pin controllers, but you may notice, hey, wait a minute, I don't see any MOSFETs. So the first thing we're going to talk about is what's going on here. Why are there no MOSFETs? Again, it's really important in electronics to get comfortable with the idea that there are a lot of variations on a similar theme, right? So it turns out this is no different from what we've got down here. It's just configured a little bit differently. So these controllers are AWV and BAC. I'm going to flip this around so you can see them better. So these controllers, 20-pin controllers, AWV and BAC. So let's try to figure out what those are and how this is configured. And we're going to use a resource we talked about previously, which is the badcaps.net forum. And here is badcaps.net we talked about before. And we're going to scroll down and see if we can find anything that looks a little bit like those ICs we showed before. And when you get to the Silergy section, you can see here's all the codes. And we had AWV and BAC. And it turns out if you go down to AWV, it's a Silergy SY8286. And the BAC is a Silergy SY8288. So now we can go to the Silergy website. So here is the Silergy SY8286 high efficiency 6 amps 23 volt input synchronous step down regulator. And you can see it's got a typical application and there are no MOSFETs. You've got an inductor, a capacitor, and V out and V in, but there's no MOSFETs. And if you look at the input diagram, you can see, aha, it's got built-in MOSFETs, and they send the signal out to the LX, or the inductor pin, which goes to the inductor. So basically it's a controller plus two MOSFETs for switching. So that's why these are only one control circuit and no MOSFETs, because they're built in. And it's the case with both of these. So if you look at the pinout for this, on pins 19 and 20, there are both tied together going to the inductor. And then pins 2, 3, 4, and 5 are tied together. That's the input 19 volts or whatever. So we've also got another pin going to the inductor. So we can check on the board and see, okay, here's pin 1. All of these are tied together to the 19 volts. You can see they're all in the same trace. And then these are tied together and going directly to the inductor. This is the LX pin. So it makes sense now that we've got this single controller that's also got the MOSFETs. So it is again converting from 19 volts down to whatever voltage here. So now if you look at this particular circuit, we've got our controller, we've got our dual MOSFETs and our inductor, and you can see this big device here, and you might think, well, this looks kind of like a diode, right? Well, it turns out you can see this 470 here, and one up here has got this 330, and it might sound like, that sounds more like a microfarad size of a capacitor. And this looks like more like an electrolytic capacitor. So it turns out, if you go through and look at polymer capacitors, you might find something like this, a Panasonic conductive polymer aluminum electrolytic capacitor. And the way it's laid out, you can see it's got the microfarads on the top with some codes on the bottom. So again, this is the output capacitor that filters the PWM signal. And that's the case with both of these. So instead of having smaller capacitors here, there are these big electrolytic capacitors filtering the current voltage coming out of these large inductors. So now that we have a better idea about how these circuits are working and how we can reverse engineer them, let's start looking at the voltages coming out of these different circuits and see if we can figure out these are converting 19 volts down to what voltage. The first thing we want to do is we want to figure out where the input PWMs are to these inductors, because the inductors are a nice big component that you can put a probe on to measure voltage rather than trying to probe these pins of these controllers or maybe the MOSFETs. As you can see here, we've got the output of this controller going to the inductor, which means there's a PWM signal here, there's a PWM signal here. Over here, coming out of these MOSFETs, there's a PWM signal here, PWM signal here. But on the opposite side of each of these inductors, there should be a flat DC. Same case here. This should be a flat DC of varying values depending on what circuit it is. So what I've done is I've gone to each one and made marks to show where the input PWM signal is on each inductor, and then the output DC. So in blue, I've got the input PWM, and on yellow, I've got the output DC. So now we can start to go in and start making measurements on each of these to find out what the voltage is. Now keep in mind, in some cases, it may be difficult to probe, like in this case, we've got this RAM here and there's a tiny space. What you can do is you can follow this, and it turns out here is the current sense resistor. So maybe it's easier to put a probe here since these are tied together and this is virtually no resistance. So you can probe here. So keep in mind, you don't have to necessarily probe on the exact location. You can follow the trace and probe somewhere that's a little bit easier. So now we can go through and we can probe on these different yellow sections with our meter or our scope and find out what the voltages are. And just as an example, I've gone through and found out that I measured 3.3 volts here, 5 volts here, 1.3 volts here, 8.5 volts DC here, and then 0.7 and 1 volt here on these different rails. So As we know, 3.3 and 5 are very common. 5 is used for USB, SATA drives. 3.3 is used for a lot of components, integrated circuits. 1.3 is probably used for this RAM here. You can see upside down it says this is DDR3 RAM, 1.5 volts. So you can see there's a trace going out of here over here. So this is probably for the RAM. 8.5 volts, not sure exactly what that's for. Maybe it's for the fan controller. And then over here we've got a 0.7 volts and a 1 volt. And it turns out over here to the left is our CPU. So this is probably CPU voltage and maybe integrated GPU voltage. But now we have an idea about what the different voltages are. And we can go through, and if we want, we can measure the blue dots with our scope and come up with the switching PWM signals. So for example, you might get a PWM signal on the input of the inductor that looks like this. You see we've got the low duty cycle, very short time, because we're trying to get the average voltage. We got some ringing. So that gives you a pretty good idea how you can start and think about the large section that has all of these different DC to DC converters. Okay, so that's it for this one. If you like any of these videos, I encourage you to hit the like button, subscribe, hit the bell notifications, but most of all, please let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.